deflections, tip loss, variable induction factors. Yes, you may choose both of them, but it can make it more computationally expensive. I've limited the number of iterations to 50 because 100 takes time. So these are the parameters. Then start simulation. So the simulation is done. You can see the coefficient of power here. So most of all of these terms can always be checked up in the user manual. Some of the major challenges that has led to the slowdown of vertical axis wind turbine development are these constraints which are presented here, which has to do with defining the wind field modeling, dynamic loading, and fatigue analysis. I must say that if a professional or if anyone is able to solve most of these challenges and to simplify them, definitely there's going to be much progress in the field of vertical axis wind turbines. Hi there, and welcome to Catering Resources. In this video, we are going to be looking at vertical axis wind turbine progress constraints. We are going to look at the swept area of a Darrieus and H-Rotor. We also look at the power that can be extracted from a Darrieus and a H-Rotor, as well as we are going to model a H-Rotor in QBlade. So you can see here under windfield modeling, there are different models for how to estimate the performance of the wind turbine system in terms of the wind direction, the speed, the behavior, as well as the power generated. So you have 1D based stream tube, actuator cylinder model, so you have 2D and 3D. You have vortex models, you have Eulerian CFD models. These are complex models that need to be defined because we are talking of triple integral. So when you have a single integral, it's easier to estimate and break it down. And even in the case of some single integral, you actually have some unknowns which make it difficult. So you have to make assumptions and iterate. In this case, for some of these actuator cylinder models, they are talking of triple integrals. So some of these things make it difficult to actually estimate the real values because these real values are required for modeling, which is one of the reasons why it's a challenge. There are several literature that you will check. They will only define these equations, but they will not solve it. So for the industry itself, solving these equations will be a breakthrough for vertical axis wind turbine development. So when it has to do with dynamic stall, blade vortex interaction, flow curvature, then VAWT wake deflection. So you see that for VAWT wake deflection, we are talking most of when you're interested in a wind farm. But for the other cases, when wind penetrates or when wind hits a blade for a VAWT, there are several interactions that occur. When the speed is excessive, you could have stall. So how are you controlling the stall? In which case, in most cases, it's a dynamic stall. It's not a self-controlled or a remote-controlled stall. You also have blade vortex because this occurs around the blade. Certain wind effects is going to occur. So you see that all of these things need to be accurately estimated. Then lastly, for fatigue, because there is constant beating of the blades, airfoils, and elements, there's constant beating, constant rotation, constant movement. There will be need for fatigue estimation on the blade itself and all the other components of this wind turbine system, because once you have the actual frequency for the vibration of this blade itself, then you know how to assign the different resonance or frequencies for all the other parts and components of the vertical axis wind turbine system. So this vibration distribution will be important in order to ensure that there is no resonance on the system unless resonance is the target. So when you are talking about the swept area of a vertical axis wind turbine, a Darrieus is similar to a H-Rotor because it's just like a simplification of similar technology, but in all cases they are lift-based VAWTs, which I've covered in part 2. So for a Darrieus, in order to get the swept area, you're talking about the diameter times the height times 0.65, which is, since you're talking of probably a parabola. Then for the H-Rotor, you're talking of H times D, which is the swept area. So coefficient of power based on experiment, because most of all these things, if the equation cannot be solved, then experiments are the way to go. Based on experiments and other calculations, the Darrieus coefficient of power is 0.25 on average, and that of the H-rotor is 0.2. So when you want to extract wind power from the air, it's good to know the wind power density of that region. So you can see clearly the countries that have better wind power potential, which is in the red. So this is from the ESA, European Satellite Agency, that provides this data. So I'll be considering mostly for Nigeria where I am, but for your own purpose, you can always consider any country. So from the blue, we are having something around 50 watts per meter square. So this is from NIMET, power density from wind map. From NIMET, within certain regions in Nigeria, we are talking of about 42 watt per meter square. So if we use this value of 42 meters, we are going to use it to estimate how much power can be captured from the air. So power capacity for production. So average power is the capacity factor times the area of motor times the wind power density. So assuming you have a Darrieus and the wind power density is 42 watt per meter square, we are going to be coming up with a power of 36.855 watts. Then when it comes to the H-rotor at 42 watts per meter square, we are coming up to 45.36 watts. So you can see the difference between both of them based on just this estimate. So basic VAWT, aerodynamics and power. So this is the basic theory from which everything is derived. So for the performance, this is the basics, but the calculations are more elaborate and a little complex depending on the approach, the dimension that you choose to follow. So following two dimension and simplifying it, the formula that comes up for the power in 2D is half times Cp times rho times the cube of the velocity, that's the incoming wind speed, times 2 times the radius times the height of the blade. So in this case, when we estimate for the Darrieus, we are getting 34.5 watts. And when we estimate for the H-rotor, we are getting 53.1 watts. So that's basically an estimate. This can then be compared with the values that are coming from QBlade. This can then be estimated compared with the values that are coming from QBlade. For example, there are 3 documents. So once QBlade has been downloaded, the free version, and it's open, and you see several files and folders. If you come to documentation, there are several folders here. So, but what is important for now is the QBlade short manual and the QBlade guidelines, although I've opened 3 of them. So this is the QBlade short manual. We'll follow it page by page in order to arrive at what we want for the vertical axis wind turbine, which is the H-rotor. The H-rotor. So you can see here, this is the second document from the first page, V.06. So if we go to QBlade VAWT module, you go to this bookmark here, you can see some certain formula. So if you read this carefully, it will help you with what is being done on QBlade. So you see here, it's talking about this part of the program provides a range of scaling and optimization functions as well. In the following, the user can choose between rotor simulation and turbine simulation. The former is dimensionless, meaning that rotor simulation is dimensionless for a range of tip speed ratios, whereas the latter one requires the definition of concrete turbine parameters such as RPM and is executed for a range of wind speed. So probably you choose turbine simulation in order to get the values in terms of watts, and you're plugging in the right values that you need to have the same magnitude with whatever you have done on hand. So there are also other means for you to validate the calculations that are done on the VAWT and the QBlade. So you can actually look at these pages in order to validate the work that has been done. So I'm only showing this because in the video we're just going straight ahead to look at how VAWT is going to work out. So I've opened here QBlade. So if you are designing or modeling, so if you are modeling a HOT, a horizontal axis wind turbine system, you'll primarily be focusing on this three-bladed structure, which is the HOT. And you see that the different options, and you even have QFM. QFM has to do with structural design of the blade. But this option, this structural design of the blade, is not available with a vertical axis wind turbine. So I just said, let me mention that. It's only available for the horizontal axis wind turbine, meaning that you need to do more work in order to be able to design the blades for vertical axis wind turbine systems. Another thing is that aside the calculations for design of VAWT, it's possible to develop models, physical prototypes of your VAWT, and then to test it in a wind tunnel. Through those means, you are able to also get data, because not all data is obtained through calculations. There are some data that can be obtained through experiments, and you'll be able to get a breakthrough. So we are starting a new project, and we pick on the VAWT. So if you look at this document, which is the short manual, so it shows you the stepwise process of how you need to generate the information you need to work on. So I think we have done this in part 1, where we show the whole model interface. So as you are going from page to page, you'll be able to pick information. So let's go straight ahead and use it. So the first thing is the airfoil. So we need to select an airfoil. So we will use NACA airfoil 0012. So that's airfoil 0012. So let's save it as, let's give it a name. So we call it VAWT simulation catchment of resources. Hold on, let's call it VAWT H-Rotor. H-Rotor. So the next thing is to get some polar information. So this is the mark number. So you can always change it. If you want user defined, you can change for what you want, even in terms of the naming system. So this is it. So we analyze. So it's going from start is minus 20 degrees to 20 degrees, which is how the airfoils work for vertical axis wind turbines when you're using an airfoil for lift based VAWTs. So you have the angle of attack and coefficient of lift, coefficient of drag. So all of these things have been estimated. So it has done a CFD for us. We don't need to save here. So let's move on to now for it to modify it for a 360 plane. So we use the Montgomery method. We extrapolate. First of all, save it as extrapolated, and we have saved it. So you saw where we saved. So let me save the document also. So we saved. The next thing is P noise. So no noise simulation in database. So we want to simulate the noise level. So noise simulation. So create. Okay, has no options. Okay, so we come to this page, options. So it's all. We want to do for all polars. All polars. which is this, all. This polar, okay, all, yes. So we create, so it has done the polars for all of them, the noise simulation. The next thing is rotor blade design. It's not really the finite element structural design, it's just the arrangement of the profile. So we go to new and we start from 0. So we're going to use a blade height of 3 meters. Add section 2, 1, add section 1.5, add section 2, add section 2.5, add section 3. So after that, the chord width is 0.2, which is fine. The radius, you're not touching the radius, but okay, we can change parameter to length. So you can use chord, you can use length, or you can use height and radius. So length and angle. So the angle is not changing, it's the same. So I think you can use length and chord width. So we don't need radius. So there's no twist. Let's say we're using 0 degrees, 0.5, 1, 1.5, 2, 2.5, 3. So aside that, we then come to the airfoil and select the airfoil and the polar. You just need to click on it and it's selected. So you may need to optimize if you are changing shape. So you can see helix blade, straight blade, but we don't need to optimize. So we'll leave it that way. So we save it. So that's the blade. Next is rotor DMS simulation. So in those user manual, you'll be able to see all of the information and the definition. So you need to define the simulation. You click define, new blade simulation, corrections, tip loss, variable induction factors. Yes, you may choose both of them, but it can make it more computationally expensive. I've limited the number of iterations to 50 because 100 takes time. So these are the parameters. We'll create, then start simulation. So the simulation is done. You can see the coefficient of power here. So most of all of these terms can always be checked up in the user manual. So for multi-parameter DMS simulation in database, so the previous one was for a few parameters, but this one now is multiple, which is going to be more complex and more time consuming. So 50 iterations is good, but if you have time for it, because this is just a video, I've used 50. You can use 100 simulations, which is what 100 iterations, which is what the program recommends. So the multi-DNS simulation is complete, and we don't need to save. So we move on. So you can see here the wattage at the different velocity levels. When the velocity is low, you can see how low the power is. So you can see the tip speed ratio is recommending what the tip speed ratio should be. So for a smaller tip speed ratio, you are going to have a higher power, which is this red line. If the tip speed ratio is high, then you're going to have a lower power. So you need a low tip speed ratio, let's say about 7. If you have 7, then you have around the highest power for the system. So if you read those documentation, you have better information to navigate this. So this is um, turbine simulation. So turbine simulation is what to give us the real values in dimension values. So you say turbine type single variable. So let's say single, rotational speed single. Let's say cutting is 1.5, cut out is 14 or 15. Later on, we'll then define the actual running speed. We'll use 4 meters per second. So we save, then we define simulation as before. So we create, then start simulation. So see, it's saying wind speed from 1 to 32. So it's going to run wind speeds, because I use 32 because that is the gust wind, that's the 30-second gust wind speed for my location. So you can use that's what I'm using it. You can always use a different value for your location. So the simulation is done for the simulation is done for the turbine DMS simulation. So next is the turbulent windfield generator. So rotor radius is 1.8. Okay, sorry, 0.9, which is what was used in the other part of the video. Then the hub height, let's say hub height is 0. Then mean wind speed is 4 meters per second. Maximum height is 3 meters. Let's just see, hopefully there will be no error with this hub height being 0. That's assuming the vertical axis wind turbine is placed on the ground. So let's create. So it says rotor radius must be less than hub height. Okay, rotor radius must be less than hub height. So hub height, let's just say hub height is, let's say hub height is 2 meters. So there's no error. So it's the wind field. So let's edit it. This has to do with the wind field itself. So maximum height should be higher than the height of the wind turbine blade. So let's say maximum height is 7 meters. So we'll create. Replace. Okay. So this is it now. So the next one is non-linear lift line simulation. So we are going to simulate the power itself on the wind turbine. So inflow wind speed is 4 meters per second. You can see this 4 meters per second. So it's using power law. Reference height, let's say reference height is reference height should be 3 meters. Sorry, yes, 3 meters. So at that 3 meter level, or let's say 10 meters, that's where you have, sorry, 3 meters, that's where you have this 4 meters per second. Because from the other calculation, we went straight to calculate tip speed ratio. Let's say tip speed ratio is, or let's just use the 9 as it was. No, let's use 2. So let's leave all the other parameters as constant, and let's create. So this one's determine what you can see or can't see during the simulation. So let's start the simulation. So you can see before it starts, let's stop it and start it again. Let's stop and start again. So we are using 4 meters per second at the reference height of 3 meters. Then we are maintaining all the other parameters. Output algorithm. So let's leave everything else constant. If you read those documents, it will be easy to navigate all of this. So let's see. So you say start simulation. Look at this. You have kilowatts. You have kilowatt, 0 kilowatts. Average power. So you see the rating is in kilowatts. So you can see that the coefficient of power is very high. Even the power that we are generating is high. It's higher than the calculations that we did. So when it comes to this point, you then need to do proper verification of all of the parameters that are used for the design or simulation of a VAWT using QBlade. Let's say we change the tip speed ratio. We change the tip speed ratio to something else. Let's say we use tip speed ratio of 10, or rather 9. Let's use 9. Wind speed of 4 meters per second at 3 meter height. So in terms of the location for the hub height, you can always read those documentation and you find it, as well as all the other information. I'm only doing this video in order to introduce to you certain productivity tools, not necessarily to show all the information. So you should be able to do a search by yourself and perfect everything that this software is capable of. And also remember, this is an unpaid version. The paid version will provide you more details, but as an entry engineer, you can look at these things and know how to make use of it. So if you have an opportunity to work in the wind power sector, you already be conversant with the interface for different kinds of wind power systems. Thank you for watching this video. This is Catchment of Resources, where we create for better living.